Are you sitting completely still? It feels like it, but you're hurtling through space on a spinning planet. Motion is never absolute, it's relative. You measure speed against your local frame of reference. Step back to a macro perspective and everything moves. To make the mathematics of all this movement manageable, physics uses a mandatory hack. We strip away the complex dimensions of massive things, like trains or planets, and shrink them down into a single mathematical dot known as a point object. This only works if the object's size is tiny compared to the distance it travels. A massive train traveling between stations is a perfect point object, but a glass beaker slipping off a short desk cannot be treated as a single point. Before you can calculate how fast something goes or where it lands, you have to lock down exactly who is observing the motion and decide if the object itself can be stripped down to a simple dot. Staring at kinematic graphs and trying to memorize what every single curve and line means is frustrating. Instead, there is a universal framework that decodes any graph instantly. Divide the y-axis by the x-axis, and you calculate the slope. On a velocity time graph, dividing velocity by time gives you acceleration. Conversely, multiply the axes to calculate the area under the curve. Multiplying velocity by time yields total displacement. By applying this division and multiplication rule, the physical meaning of the graph reveals itself. You don't have to rely on rote memorization anymore. Constant acceleration is governed by 5 equations connecting displacement, initial and final velocity, acceleration, and time. This is the SUVAT engine. To operate it, identify 3 known variables. With 3, you can calculate the remaining 2. Throw a ball straight up with an initial velocity of 29.4 meters per second. Gravity pulls downward at 9.8 meters per second squared. We define the upward direction as positive. Because gravity opposes this, its acceleration must be assigned a negative value. Pause the video. Which equation finds the time to reach the peak? At the exact top, the ball stops, making final velocity 0. Using v equals u plus at, substitute 0 for final velocity and negative g for acceleration to solve for time. If you mix up your positive and negative signs, the ball will mathematically accelerate into space instead of falling back down. Trusting those directional signs keeps the physics tethered to reality. Let's put this into a single straight line. The formula for relative motion says the velocity of object A with respect to object B is simply velocity A minus velocity B. Imagine a mother and father standing 50 meters apart on an airport conveyor belt, moving at 9 kilometers per hour. A child runs between them. From the mother's perspective, she and the child share the same moving reference frame. Because they are both on the belt's motion drops away entirely. To her, the child is simply approaching at 9 kilometers per hour. Now look from the stationary ground, through the eyes of the dog. If the child runs at 9 kilometers per hour in the opposite direction of the belt's movement, the 2 velocities cancel out. To the dog, the child is running on a treadmill, completely stationary in space. Here is the puzzle. The mother sees the child running quickly, but the dog sees the child standing still. If the speed changes depending on who is watching, does the time it takes the child to reach the mother change too? The answer is no. In classical mechanics, time is independent of the observer's frame of reference. Whether you are standing on the belt or watching from the grass, the interval required for the child to cover the 50-meter gap remains the same. While measurements of velocity and displacement are relative to your chosen frame, the duration of the event is a constant that every observer can agree on. Let's lock in the 3 absolute rules of one-dimensional motion. 1. A horizontal line on a position time graph means the object is at rest, 0 velocity. 2. The area under a velocity time graph always equals total displacement. 3. Total distance can never decrease. Capture these rules for your notes. Keep your reference frames clear, watch your signs, and the mathematics of motion will always work out.